Taking a look at practice question set number 5, which on your Physics 30 and 13 pages document you can see as concept number 16, conservation of momentum in 2 dimensions. The first question says, at a coal mine, a train engine bumps an empty hopper car that has a mass of 10,000 kilograms, such that it rolls at a constant speed of 2 meters per second under a storage bin. Hopper car triggers an electromagnetic switch, drops a load of coal onto the hopper car, and you scroll down to see what the question is. It says, what's the velocity or the speed of the hopper car right after receiving the load of coal? So here's what's going on here. Let's draw this out, because to me this seems like a 2-dimensional problem. We've got a hopper car with a certain momentum this way just before the collision of the coal in the hopper car. And then we've got coal moving this way just before the collision. Agree? Somebody this morning said, well, can we look at the coal being at rest up here? Well, if we say the initial velocity of the coal is 0, then that's not an isolated system, right? We have to look at it just before and just after the coal hits the hopper car. So it's moving downwards. It's clearly moving downwards. Okay, where would you expect, right, in the absence of common sense, okay, I shouldn't say don't use common sense here, but just pretend for a second you don't have common sense. Or as Mr. Kader and I like to call it, uncommon sense, because lots of people don't have common sense. It's more uncommon sense than common sense. But anyways, in the absence of common sense or uncommon sense, whatever you want to call it, where would this hopper car and coal combination go? Yeah. Isaiah says it would go underground, like down and to the right, right? Make sense? Like as a 2-dimensional collision, like if the Earth wasn't there, it goes down and to the right. If this is a collision that takes place in some kind of space or something when the Earth isn't below this hopper car, it's going to go down and to the right. Agree? Now, the fact that a train engine bumped an empty coal hopper is really irrelevant, right? That's just what got the hopper car going at 2 meters per second. We don't care about how it got moving that fast. It was moving that fast just before the collision. Okay, let's treat this as an x and y component problem. Because we do have a component that's to the right and a component that's downward here, right? So my x component, we're going to say what? M1 V1I plus M2 V2I equals, we'll say M total times VF. But I'm going to make this 0. How come? Didn't I just say the coal wasn't at rest? Didn't I just say the coal was moving before the collision?
It doesn't have any x.
Right. It doesn't have any x velocity to it, so it doesn't have any x momentum to it. So it is 0 for the x component. M1 that's the hopper car. It's 1 times 10 to the 4 times V1I, which is 2.0 meters per second, equals the total mass. When we add the hopper car and the coal together, it's 2.2 times 10 to the 4 times VF. We solve for VF here. It works out to be 0.909 meters per second. How many people got that for the x component? Okay, how many people got that for the final answer? How can the x component be the final answer? I don't have to do y? Isn't there a y component here to this?
Because it's on the ground and all the force applied by the coal is applied back by the Earth.
Okay, be careful of that. Okay, that'll work actually. Yeah, that'll work. Here's the way I want you to think of it though. If the coal is going downward and it hits the hopper car, it wants to push the hopper car down, right? But what does it want to push with the hopper car downward? The Earth. So don't write this down, okay? Don't write this down. Let's start doing the y component for a second. There would be, object number 1 would have 0 momentum on the y-axis. Object number 2 would have, this is the coal. If you're going to do the y-axis, and when the coal hits the hopper car, it moves the Earth with it, then mass total here, this time for the y-axis, would include the mass of the Earth, right? which is 10 to the 24 kilograms. If you include the mass of the Earth and you solve for VF for the y-axis, VF is going to work out to be 0. I don't know, like a lot of zeros before you get a non-zero digit, right? So in other words, the y-axis is like effectively nothing, right? The Earth gets pushed down, yeah, whatever, like who cares? It gets pushed down a negligible amount, right? Sometimes if you're standing nearby, you feel it shake a little bit, right? But like the Earth itself isn't really going to move anywhere, right? So if you refer back to your Physics 30 and 13 pages document, page 3, topic 16 says conservation of momentum in 2D. You go down to the very last thing, K, says problems involving the Earth. That's what I'm talking about there, problems involving the Earth. When the y-axis ends up having to include the Earth, then just do the x-axis. Don't even bother trying to do the y-axis, because you know it's going to turn out to be so small that it's not going to matter. Does that make sense? Problems involving the Earth, don't bother with the y-axis. Now, the exception to that would be, I suppose, if another planet collided with the Earth and the masses were comparable, right? But any kind of situation on the Earth, the y-axis wouldn't matter. Good? Okay, I want to skip to the third question now, and then we'll come back to the second question. Multiple choice question number 2, or the third question, says a hole is drilled into a boulder, has a mass of 250 kilograms, explosive charge is placed in the hole, the boulder explodes into 3 pieces at right angles to each other. What's the magnitude of the momentum of the 90 kilogram piece? Which way are they going? Right angles, east and north, south and west? I don't know. Because we're only looking for the magnitude of the momentum, it doesn't really matter. It would affect the direction, but it's not going to affect the magnitude, right? As long as we draw it at 90 degrees. So here's how I do it. Okay, I said piece number 1 is going off this way, 110 kilograms, 4.0 meters per second. Piece number 2 is going off this way, 50 kilograms, 10.0 meters per second. And now piece number 3 is 90 kilograms. And it's going to go off up and to the left, right? We know that. We don't have any funny angles here. Like we're gonna find one. We could find a funny angle, but we don't have a funny angle, so nothing to worry about there. We just go straight to our x and y components here. 0 initial momentum equals 110 times 4 plus, anyone? What's the x component of this one? 0 plus 90 times V3F. That worked out to be negative 4.888. Zero initial y again is equal to I said zero momentum here because that's on the x-axis, plus 50 times negative 10 downwards, is 90 times V3F. Oh, I'm waiting here to get to something. Like questions like this. You see how many of you guys got this. 4.888 to the left. 5.5556 up. And we combine them. We don't need to find theta there, right? So we're just saying find V there. Works out to be 7.40037. 7.40. How many people said A? But it's wrong. How come? Regan, why is it wrong? What did we just solve for there? The velocity. What are we looking for? The momentum. Right. Isn't that so dirty that they put that as an option there? Yes, it is. But get used to it. Because they're dirty. That's what they do. I don't know how many of you guys noticed up on the board here this morning I wrote this. It was specifically in reference to this question, but we see it not just in this question. We'll see it again. Situations like this. RTQ, ATQ, what does that mean? Read the question, answer the question. Okay, read the question. The magnitude of the momentum, all right? Answer the question. Get the momentum, not the velocity. How do we get the momentum from this? It's not hard. As long as we recognize that we got to do it. We multiply m times v, and when we do, we end up getting 666 kilograms meters per second. That is a devilish question that we have there, eh? So the answer is C, not A. Read the question, answer the question. Now, there is another way that we could have tackled this slightly different. Not much, but slightly different. I found the final velocity of the third piece, and then combined velocities, multiplied it by mass. I could have found the final momentum of the third piece, x and y, and then combined momenta and got my answer right away, right? Make sense? So instead of solving for V3F, I solve for P3Fx, P3Fy, and then combine those, and then I'd be done. I don't think that necessarily one way is quicker than the other, but just two slightly different ways of thinking about it. Finally, this is multiple choice question number 1. Sheet of curling ice. Who's a curler here? Anybody curl?
What did you say?
So there's a red curling rock traveling straight down a sheet of ice at 0.36 meters per second, contacts a stationary blue curling rock. If it hits it straight on, then the blue curling rock just goes straight ahead. But if it's what we call a glancing collision, kind of hits it on the side, then they go off at different angles, right? We want to know here in the end, we want to know what the speed of the red rock is after contact. So clearly we've got a funny angle here. In fact, we've got two funny angles. Right, we've got 67 degrees and 23 degrees. The only thing we can do anything with is this one. We can't do anything with the 23 degrees. Okay, how come? We don't know what the hypotenuse is, right? We don't know what the number is that goes with it. So don't worry about that. There's nothing you can do with it. By the way, this angle right here that's circled in red here, this is a situation where I call it a situation where we're given the unknown angle, which is really a paradox. It doesn't really make sense. We're given the unknown angle. If it's given to us, it's not really unknown, right? But usually that second angle is unknown, right? This time we're given what is usually the unknown angle, right? If we didn't have that angle, could we solve this problem? Absolutely. So if you want to pretend you don't even have it, go ahead. Just pretend it's not even there. There is a way to do it as a shortcut, knowing what that is, but we'll do it without the shortcut first. And then I'll just show you what we do if you want to take the shortcut. Okay, so we got a funny angle here. Got to get rid of it. Take it off to the side up here. 0.14, 67 degrees. Okay, let's solve for x and solve for y here. Using cosine x is 0.0547 and y is 0.12887. Block it off because that's what we always do. Maybe redraw this. This is 0.0547. Pretend we don't have this. Okay, because it's gone. That was the whole point of taking it off to the side, right? Was getting rid of it. And then we do our thing here. M1 V1I plus M2 V2I equals M1 V1F plus M2 V2F. Good news here. What is it? It's the news that I, like, every time I see one of these questions, I want to see it, but we don't usually, it doesn't usually work out for us. What is it here, Taylor? Yeah, because good, exactly. The masses are the same. I don't think they even tell us what the mass is. Oh, yeah, they do. 18.8. So if you want to use it, go ahead, but you don't need to. V1I is 0.36 plus 0, because object number 2 is at rest. The blue one's at rest. V1F, that's what we're looking for here, right? The red one, yep. Plus V2F is, for the x component, 0.0547. How's that going to be? 0.3053? And do my y-axis, even easier. What's the initial y-axis? 0, because it's all this way, right? The masses cancel again. V1F plus 0.12887 for the y. And then we combine them, right? V works out to be 0.33 meters per second. And the answer is C. How many people got that? How many people did it just like that, or pretty much like that? Anybody take a shortcut here? Anybody spot something partway through? Yeah? What'd you do?
I don't really know if I did it 100% accurate. It's just that, like, if you take the two complementary angles, they equal a 90 degree.
Yeah?
So then I don't really remember too much of it.
Okay. But did you get the right answer?
Yeah.
Okay. Okay. So given that angle, that probably would work out, but without a little bit more detail, it'd be hard to say whether that's a luck or an every time thing. Probably an every time thing. Here's the shortcut that I spotted here that you can take or not take, whatever you want to do. I'm going to look at, I'm not going to do that. That's gone. I'm going to erase one of the components too, either the x or the y. I'll erase the x actually because the y seems easier, more straightforward. And then I'm going to say the x component of that resultant vector, I don't know. The y component of that resultant vector, I know is 0.12887. In the angle, I know to be 23 degrees. Anybody see where I'm going with this now? If I have opposite and I have the angle, then sine 23 degrees is equal to opposite over the hypotenuse. And lo and behold, it's 0.33 meters per second. So if you're given the value of the, we'll call it the unknown angle, what's usually unknown, there's a shortcut. But you never have to take advantage of that. So if you don't notice that, or you're just not comfortable with doing it a little bit different, then don't do it different. It takes you a little bit longer the other way, but it's just as correct every single time. But if you want to take advantage of the shortcut, go ahead and do it that way. Because you have 6 hours to do this exam now, which I wouldn't suggest for a second that you take anywhere close to 6 hours to do it, but because you have all the time you want, you have some time to do it both ways. Nice little check to see if you've got the right answer, right?